We're going to do more partial fractions, and really we're not actually going to do anything different than we did last class. We're just going to do another example. We will actually do the integration step here as well. If I look at this particular problem, I know I have a rational function, which is a polynomial over a polynomial. So this is a good candidate for partial fraction decomposition. The denominator factors nicely, which also makes it a good candidate. If we can't factor the denominator, we can't use partial fraction decomposition. I also noticed that the power on the denominator is x to the fourth, and the power in the numerator is x cubed. So this also makes it a good candidate for partial fraction decomposition. The power in the denominator is lower than the power in the numerator. If not, we would have to start out with long division, which we'll do next class. But before I jump into partial fraction decomposition, let's verify that we cannot do u substitution here, because if we could do u substitution, life would be much easier. If we were going to do u substitution, we would have to pick our denominator to be u. I'm going to go ahead and multiply that out. So my du would be 4x cubed plus 9x squared. The 4x cubed looks promising, but everything is added here, and we don't have the rest of this in my du. So my numerator is not going to cancel out with my du, which means that u substitution is not going to work here. Okay, and like I can't factor anything out of the numerator and make that cancellation happen. So we're going to do partial fraction decomposition. I'm just going to do the decomposition on the inside, and then I'll go back and integrate. So I'm not going to write my integral symbols until I have done the partial fraction decomposition. So we're going to need to write 4x cubed plus 2x squared minus x plus 6 all over x cubed times x plus 3. That x cubed means that I'm going to get an x squared and an x cubed term, because remember, if I have anything like x plus 1 to a power that's bigger than 1, then I get as many terms as that power. So that power is third degree, so I have 3 terms. And these are going to be a, b, c, and then I'll have d over x plus 3. Okay, my common denominator here is x cubed times x plus 3, so I'll multiply everything by that. My left-hand side leaves me with this messy expression. Oops, if I can write it correctly. Okay, so now when I multiply a by my common denominator, I'm going to be left with a x squared times x plus 3. When I multiply b over x squared by it, I'm going to be left with bx times x plus 3. C is just going to leave me with an x plus 3 and d with an x cubed. Okay, so now I notice that there are 2 numbers that are going to be nice to plug in that will cancel lots of things out. If I plug in, and I can go back up here and see what those are. So if I plug in x equals 0, that will make the x cubed or the x pieces go away. And if I plug in x equals -3, that will make a lot of terms go away. So I'm going to plug in those values. So if x equals 0 and if x equals -3. Okay, so if x equals 0, my left-hand side is 6. This term, and this term are all 0. So this is the only thing that's not. I'm going to be left with c times 3. So 3c dividing both sides by 3 gives me c is 2. Okay, now if I plug in -3 for c, I'll let you do the calculation, but on the left-hand side, I'm going to get -81. This term, and this term are all going to be 0. Then d times -3 cubed will give me -27d. If I divide both sides by -27, I get that d is 3. Okay. So now the problem is that those were the only 2 easy numbers to plug in that canceled everything out. Because we had a term to a power, we're always going to end up in the scenario where we have to choose other numbers to plug in for x. And at this point in time, you can pick your favorite numbers to plug in for x. We're going to have to use 2 different numbers here because we still have 2 variables we're solving for. So you can pick your favorite numbers, 5 and 27, 72 and 42, 1,000,000,001 and -10. I'm going to pick 1 and -1 because those numbers are a little bit easier to work with. We just have to pick things we haven't already picked. So if x is 1, what's going to happen? My right-hand side is going to be 4 plus 2 minus 1 plus 6. I'm going to have a times 1 times 4. So I'm going to have 4a. B, I'm going to have a 4b as well. I'm gonna have C times 4, but C is 2, so 8 times, or 4 times 2 is 8. I made that mistake the last time I recorded the video, I wrote 8 times 4, but it should just be 8 total. And we have D times 1, D was 3, so 3 times 1 is 3. Okay, so now if I rearrange things here, I'm gonna have 4 plus 2 minus 1 plus 6, and I'm gonna subtract these guys over, so minus 11. So that is going to give me 0 is equal to 4a plus 4b. If I divide both sides by 4, I get 0 is a plus b, and this tells me that a is negative b. That doesn't actually give me an answer for what a and b are equal to yet, and that's because we still need one more equation here. And then when we pair it with the next equation, we'll figure out what a and b are. This will be like a system of equations. So let's plug in -1 now. Again, if you plugged in -10 billion and 1 right now, that would be okay as well. So this is going to give me -4 plus 2 plus 1 plus 6 is equal to, so let me be careful here. So -2 plus 3 is 2. -1 squared is +1, so I'm going to have 2a. Then I'm going to have minus 2b plus 2c, so 2 times 2 is 4. Minus d, d is 3, so minus 3. Okay, so now let us solve this. So I'm going to have -4 plus 2 plus 1 plus 6 minus 4 plus 3 if I move that stuff over. So I get 4 is equal to 2a minus 2b. I know that a is negative b, so I could say 4 is negative 2b minus 2b. And so this looks like 4 is negative 4b, and so b is -1, and then a is the opposite of b, so a is 1. Okay, so at this point, you're like, oh, okay, I've done all the work I need to do in this problem, but no, you haven't. We still have to go back up, plug our values in, and anti-differentiate. So let's see what we have. So we had a over x, so 1 over x, plus b over x squared, so that'll give me -1 over x squared, plus c over x cubed, c was 2, so 2 over x cubed, plus d over x plus 3. Okay, so this is the thing that we're trying to anti-differentiate. Some of these pieces will be easier than others. So let's do this. So 1 over x is going to give me ln of x. This piece to anti-differentiate, let's rewrite that as x to the -2. So I add 1 to the exponent to get x to the -1, and I divide by my exponent. So I'm going to have this negative divided by a -1. So that's going to give me a positive. And then this one is 2x to the -3. So I add 1 to the exponent to get -2. And then I divide by the -2. So 2 over -2 will give me -1. This one here, you could do an easy u substitution, making u x plus 3. So my du is just dx. So I get integral of 3 over u du. That's just, you can take the 3 out, 3 times 1 over u du. So that's just going to be 3 ln of the absolute value of u and plus c. Okay, so we usually have a lot of natural logs in these problems in our final answers when we anti-differentiate, but then sometimes we have these other terms if we had x to some power that was not the first power. So long problem, but hopefully the process makes sense.